Thank you very much. My name is Nadav Keren. I'm advised by Gil Einziger and Gabriel Scalosub, and we are from Gurion University of the Negev. And I'm going to present the paper Latency Aware Caching with Delayed Hits from Bursty Traffic to Pipeline Architectures. So I will start over with some motivation. I will go over our contribution, which is 1, a new caching architecture called Adaptive Pipeline Cache, and 2, a new caching policy called LBU. And then I will finish with experimental results that will show our benefits. So let's start by understanding what is latency-aware caching. So let's consider the following setting. We have distributed object storage with different locations, varied latencies from 100 millisecond to 1000 millisecond, and a single cache at the user side. We need to understand that when we miss an item in the cache, not all misses are the same. Some misses pay more than others. And I want to point out something that I won't talk about now. I will explain it later. Bursts may be an issue. So let's look at the current pain points when it comes to latency-aware caching. So the current pain points are that the algorithms are ad hoc designed. They are workload specific and are not always adaptive. They are built as monoliths, which means that if I want to put a new signal or a new signal or a new locality into the mix, I need to build it from bottom up. That means it's hard to extend, hard to maintain, and hard to implement. On the other hand, our solution is the adaptive pipeline cache. It's modular by design. It's built from simple building blocks. It's almost plug and play. And it's most importantly adaptive, which means it's workload aware. So we get consistent performance across the board, as I will show in our results. So let's understand what is the pipeline cache itself. The pipeline cache is composed of several blocks. Each block is performing according to its unique eviction policy. The cache order, the block order, is predefined by the user. And each block is allocated a number of quanta. Each quantum is composed of k items, which are unit-sized in our model. And the total cache size is the sum of the allocations of all the blocks. So what happens when a new item arrives to the cache? Let's focus first on one single block. Let's look at block J. When block J is offered a new item, ij, it needs to decide whether to accept it into the cache in the expense of another less valuable item or reject it. In any case, it moves an item to the next block. This next item is called the victim of the block J. So now, when we get an item to the cache, it's first being offered to block 1. Block 1 decides whatever it decides and evicts a victim that goes to block 2. Now, we go with this same process through the blocks throughout the pipeline until we reach the last block. When the last block makes its decision, it evicts the item completely from the cache. This is the cache victim, and it's no longer in memory. So let's consider the following scenario. We have a pipeline with only 2 blocks, an LRU block and an LFU block. And we want to understand which configuration will be better. One configuration is LRU heavy configuration. That means that the majority of the space, the allocation of memory of the cache is going to be at the LRU, and the minority is in the LFU. On the other end, we can have something that is LFU heavy, a small LRU and a big LFU on instead. And this question is answered by another question. What is the workload? We need to understand the workload and what the workload needs in order to understand which configuration is better. So what we need to do is at runtime, we try to adapt to the best performing configuration. We do it by using a hill climbing process to continuously adjust allocations at runtime. So I'm going to go over now a design challenge that inspired us to do this work, factoring delayed hits. This topic has been studied in previous work, So it's not a new idea. But let's go over the model in order to understand what is the problem here. So let's start with a classical caching model. In classical caching, we ignore the item availability in the cache. We assume that after we get a cache miss and we bring an item to the cache, it instantly becomes available in the cache. So what happens is, let's look at an example of a sequence. We get a request for item A. Item A is not in the cache. So it's a cache miss, and we need to bring the item to the cache. Now we get another request. This request this time for item B. Item B is not in the cache, and we get a cache miss. The next request is also for item B. Item B was a miss a millisecond ago, and now it's in the cache according to the model, which means that this is a cache hit, and we don't pay for it. So are the requests for A and B that come after that. So this is the classical model. When we are talking about latency-aware caching, we need to factor in that items are not available at once, and the item availability in the cache can differ. So let's look at the same sequence. We get an item A, a request for item A, and it's a cache miss. Now it takes some time in order to be available in the cache. Now we get the request for item B. It's a cache miss. It also needs some time to arrive to the cache. And when we are looking at the following requests for B, it arrives while B is still in transit, which means that I cannot serve it from the cache. So it's not a cache hit. But it's not exactly a cache miss because it's in transit. I'm fetching it. I'm not going to pay the full price for this request. So this is called a delayed hit. It's not a miss. It's not a hit. It's something in between. The following request for A comes after A is available in the cache. Now we can say that the request for A is a true hit. We are not going to pay for this request. And the next request for B is also a delayed hit, but it is less costly delayed hit from the previous one because it's closer to the time it's available in the cache. What I want to stress here that we pay more for item B. Item A paid only one latency in order to get into the cache, but item B paid the latency and 2 delayed hits that it had to pay, which means it's more expensive. And if B arrives in burst always, I want to keep it in the cache. And this is what leads us to the next part. We are going to try and incorporate a new policy into existing policies. So we are going to create a new specialized policy and put it at the end of a pipeline in order to get something better than the sum of its parts. So we start by using existing blocks, LRU star and LFU star, which are latency-aware versions of LRU and LFU introduced in previous work. And what we are going to do, we are going to add a new block, which we call LBU, the least bursty used policy, which is going to be at the end of the pipeline. It is specialized policy. It is capturing only bursty items. That means that in the previous example, we are going to try to capture item B. It introduces a new scoring metric for its own internal usage, and it's very situational. And I want to stress out now and emphasize that LBU is not a silver bullet. It's not trying to solve everything. It just captures something new and captures only that. And this is the important part. What I'm going to show you now that this configuration, this configuration is going to get us great results. So let's talk about the experimental settings. So first of all, we compare ourselves across 13 diverse traces from IBM, Meta, and Twitter, which were augmented by adding latencies of real-life remote storage configuration measured in previous work. What we are going to do, we are going to perform a grid search for each of these traces in order to find the best static RFB pipeline configuration, and we are going to use it as a baseline for the next stage. It also gives us some knowledge about the characteristics of each of the traces. For example, if we are looking at ABM12, we can see that is more burst inclined, so the LBU gets the majority of the allocation of the configuration. IBM24 is more frequent aligned, so we get more LFU instead of LBU and LRU. IBM29 is all about recency, so we get nothing but LRU. And the nice thing is to look at Twitter28. Twitter28 shows us that there is no single policy that clearly dominates this trace. That means that this is exactly the scenario where our approach adds the most value to the mix. So we compared ourselves to 12 competitive policies. We judge them by the average request latency across the traces, and this is compared to the baseline I've shown in the previous slide. I want to point out LBU. LBU is performing poorly on its own, and it is expected. It was designed to be complementary, not a standalone policy, and this is the important part. Now we are going to look at what happens when we are using our architecture. First of all, we start by not using the LBU to see that architecture and our adaptive approach is beneficial, and we see that it outperforms on average all other algorithms. And when we add this LBU, we get state-of-the-art performance, which is 10% better than LRB, which is a very impressive and complex algorithm. And we also get the lowest standard deviation, which means we are the most consistent out of the all. The last thing I want to show is another experiment that we conducted in order to understand better the behavior of the cache when it needs to adapt. So what we have done, we've taken three traces, we call them trace A, B, and C, and we concatenated them into one trace. Trace A, trace B, trace A again, and now we get a trace that changes rapidly across the workload. And what we can see that adaptive RFB pipeline outperforms the best static. And I want to stress here that it is the best configuration that was chosen with full knowledge in advance about the trace, and we still outperform it. It means that we are doing some changes on the fly that make our performance even better than what we could have done if we have known the trace in advance. So let's look a bit under the hood of this experiment and understand what happens. First of all, what we are seeing here is the percentage of the cache allocated for each of the blocks as a function of the event number. And we see the different traces that were concatenated here. So when we are looking at trace A, we see that at the beginning, the LBU is not beneficial, so the adaptive approach shrinks it to 0. We have no LBU at all at this stage. Once it becomes beneficial, the algorithm allocates memory for it, as we can see in the middle of trace A. When we move to trace B is very recency biased, so it's rapidly changing to being only LRU. We get almost no LFU and LBU in this part, which means that we are trying to capture this locality. Trace C, on the other hand, is very bursty, so what we are getting here is a large LBU trying to capture the locality that is present in the workload right now. And the nicest thing that I want to point out that we are putting trace A again. The algorithm doesn't know that this is the same trace. What we see here, it's almost the same picture in both of the cases, and they differ only because of we have no items in the cache when it starts, and we have items in the cache. It's a full cache when we start the second iteration of trace A. And we get almost the same picture. We get almost the same allocations. It means that our algorithm is consistent knows to understand the workload on its own and perform not randomly on the trace itself. So what I haven't talked about in this talk is the design and implementation details of LBU. I haven't talked about the scoring of the LBU or the LBU structure. I haven't talked about the hill climbing process or the optimization we've done using sampling. But what I've done, I've shown you a new state-of-the-art caching architecture, which is modular, adaptive, and latency aware. And a new caching policy specialized for burst that allows us in the mix. So I'm Nadav Keren. This was my talk. Thank you for your time. Our artifact is available and reproducible on GitHub. Questions, please.